Hey, hello everyone. I'm glad to welcome you at the first event in 2021. It's going to be a small meetup. We have only one speaker, but I hope that it's going to be helpful to those of you who work with some natural language processing. If during presentation you will have some comments or a question, you can use live chat and ask your questions there. After presentation, I will read some question and we will talk about it a little bit more. If you watch this presentation in record, you can use comments. We also going to check comments after presentation, and if so, maybe answer some additional question or some complicated question. Also, we'll try add some additional links to additional materials in comments or in description to this video. And yeah, as usual, I welcome today's speaker. It's Elyes, who are going to talk about data augmentation in natural language processing. Sorry. Hi, Elyes, you can start sharing your screen and start your presentation.
All right. Thank you so much, Sergey, for the introduction. And I'm happy to be the speaker and to be one of the first speakers in this session. So let me just remove the thumbnail video. Right. So, and also I'm really happy to be the first speaker in 2021. So I have to double down and give some great content for the audience right there. So everyone, thank you for being here. My name is, as introduced, Elyes Manai, and I'm a machine learning, I'm a Google developer expert in machine learning. And today's talk is going to be about data augmentation, which is specific to NLP. So what it is, why it's important. Data augmentation is more widely known for computer vision. So what about NLP? When should we use it, etc.? So if you are working on a project like that, I hope that this will be useful for you. Now, as usual, please feel free to comment any question, add any questions in the chat while we are doing this. And if there's anything that really has to be answered, well, Sergey will tell a question to me. Otherwise, we will have some time in the end for some Q&A. All right, with that, let's get right into it. A small presentation. So my name, so I am actually a consultant, a teacher, an expert in machine learning, as I said. And for those of you who might be interested, I used to work as a machine learning engineer in FabSkick, which uses AI to help in recruitment and human resources. And then I went on to work in InstaDeep as a deep learning researcher, research engineer. And that's where I focused on NLP. And that's where the problem of data augmentation actually occurred and where this presentation has come from. So it comes from an experience of a real project that you've worked on. So now for those of you who are not yet into the domain or are into AI, but not in NLP in particular, let me give you a small introduction, which will build up to the question of why we need data augmentation. So some of you might say we don't need that. There is a specific reason why we do, and together I need to make a small introduction. So for those who don't know, NLP is natural language processing, which is a subfield of AI, which focuses on making robots or computers understand better human language, which can be text or sound. And you have, for sure, used some application of this, like chatbots, translation services, or autocomplete. And these all are sub-applications and many, many more of NLP. Now, the main focus and the main issue, and let's say the main problem of NLP is in the end, how to make it so that a robot or a computer in general can understand human language. And why it's such a problem? Well, because computers understand in binary language, so it's zeros and ones, and it does math and calculations. While text is not math, so text is words and letters have semantic meaning. And so how can we make it so that a computer understands the meaning behind the text? That is the core piece of NLP. And to do that, most of the research and the work is trying to find a representation and numbers that can represent that text and encode it from text to numbers. And this is what we call representation of text or text representation. which are numbers or vectors that can somehow represent words, sentences, and documents. Now, this is the main core of NLP, and it has evolved a lot across time. You may know of the ASCII coding, which is one of the most basic and encoding algorithms, which assigns to each letter a certain number. And this is what's currently used for keyboards, yes, but then if you want to use it for real applications like chatbots and more advanced techniques, well, this might not be as helpful. So we evolved from that to trying to make what we call a bag of words, meaning that we take a chunk of text, we then divide it into individual words, and then we calculate the occurrence of each word. And then from there, we can remove the filler words like it and the and whatever else, and just let the juicy parts. And then we can say, all right, so this chunk of text is talking about this specific topic or something else. So this is some way that's still actually useful if you want to, for example, do some data mining and analysis, etc., but not much beyond that. Afterwards, we had label and one-hot encoding, which were really useful, especially for normal machine learning and predictive analysis and predictive machine learning, which aims to transform each word into a number if we are on label encoding. So as you can see, apple, chicken, broccoli became 1, 2, and 3. And the one-hot encoding tries to transform them into vectors. So as you can see, apple, chicken, and broccoli went from being values of a single column to becoming columns in themselves. And now why we did that? It's because in label encoding, it's easier, yes. However, when you do machine learning, it's trying to understand patterns under the data. And if we have an ordered list of 1, 2, 3 up to X, well, the computer will somehow understand that the higher the number, the more it is. So for example, chicken is 2 times broccoli, or chicken is 2 times apple, or broccoli is 3 times apple, which is nonsense. So it's creating some sort of confusion. And that's why one-hot encoding came in, and it basically says that instead of having only one weight, only one feature in the machine learning model to learn, and has to adapt with the numbers, well, we will give a weight to each column. So we will have a weight for the apple column, a weight for the chicken one, a weight for the broccoli one. And then when we want to work on apple, it will be the weight times 1 and then the rest times 0. So it will not affect the overall result because it will not be taken into account. Now, this has helped a lot to work on machine learning and predictive analysis, like predicting a number, predicting a class, whatever it is, because it allowed us to feature engineer the text that we have. However, in NLP, it does have some problems, as we cannot use this for semantic meaning, as all the vectors are zeros and ones with only one, and so they are equidistant. We cannot do like the similarity measures. So honorable mention goes to TF-EDF, which was one of the most used, for the longest used algorithms for search engine. Basically what it does, it takes a lot of documents, it takes a query from you, and then it tries to query that sentence and try to find which documents have the best scores for your query, and so it will list to you the documents in an ordered fashion. So basically what Google is doing, so a search engine. However, this has now become outdated. Now, these are all different ways to encode text into something that the computer can understand and work with. And it continues to evolve as we are progressing and wanting to make better and better apps. Algorithms also become more and more advanced. And the real game changer has appeared with the artificial neural networks. So you may already be familiar with the ANNs, which are now the backbone of deep learning and AI. And it's actually this architecture that managed to make one of the first breakthroughs in machine learning in NLP. And why is that? Well, you need to understand that ANNs are trained to basically optimize whatever data they have without caring about the input. And so they actually used the architecture, which is really efficient, and made what we call word2vec. And word2vec is one of the most, let's say, one of the most widely used for a while techniques in machine learning and NLP, which was based on neural networks, and which says that the meaning of a word can be inferred by the company it keeps. What Thomas Micallef in 2013 meant by this is that instead of giving one vector, which is, let's say, ones and zeros to a word, let's give them a set of numbers that change depending on the context. So if, for example, let's say the word bank, if you say river bank, it does not have the same meaning as, for example, national bank, although it's the same word. So it's so word2vec proposed a method to make a vector representation of words. So for example, I ate an apple. For each word, we will get a vector, as you can see, which are generally 200 to 300 floats. And these actually change with the context. So if you train your model on different sets of text, even though they have the same words, you will not get the same vectors because they were not used in the same context. One could be general or business English, the other could be medical English. So the words would not be used in the same way. So this is what actually gave birth to the term word embeddings. So what we are now using, deep learning NLP and the most advanced parts of NLP are based on word embeddings or sentence embeddings or paragraph embeddings or even document embeddings, which are basically just vectors that can compress the data, the information of a given word or series of words given their context. So they are way better than just one-hot encodings, and it gives you an idea about the words that the words that are in the same vicinity. And this has allowed us to now do math. Using this, we can now project our vectors on a multidimensional plane and do similarity measures to see which words are in the same vicinity, so they might be used in the same context, which words are used, let's say, as adjectives, which words are used together. And this has allowed us to get a lot of better results in NLP tasks. So word2vec was one of the first breakthroughs. And it did not stop there. Afterwards, we've got what you call RNNs, which are the architecture on the left. So RNNs are a type of ANNs which have what we call a recurrent mechanism. So basically, while word2vec only works on a single word, so I and then ate and then N and then apple, RNNs can get the sequence of text before the word. So for example, for apple, you will get as input I ate an apple, I ate N, and the output is apple. So now it can get a sequence of text and it can create the vector that you see on the right, but now not only based on the word that's right before it, but on the sequence right before it. And so RNNs, with the most basic version of them being the vanilla RNN on the left, and then more advanced deviations called LSTMs and GRUs, which are also RNNs, have managed to allow us to get better results at NLP, especially on longer sequence of text. So for example, text generation, or for example, document similarity. So it has allowed us to get another breakthrough and to get better results on NLP. Now, let's talk about these past years, because in the past 3 years, there have been an even bigger breakthrough in NLP, and this is where the real problem begins. As you can see, this is a graph of the number of papers presented at ACL, one of the top NLP conferences, between 2000 and 2000 and let's say 20. And you can see that it's gradually increasing with a spike at the end. Well, with a spike. Well, this part between 2002 or 3 and 2018, where we can see a big increase, was the LSTM period, so the RNNs period. So this is the part where most research was focused on RNNs, LSTMs, GRUs, and they were getting the best results. But then in 2018, a new paper came out, which was called Attention is All You Need, which presented a new mechanism called attention and a new architecture called transformer, which is the one that you are seeing on the right. And the transformer architecture is different from RNNs. It does not have the sequence mechanism. It works in parallel, and it gets way better results in the end. So much so that, as you can see, there has been a spike in number of papers since they are now recreating everything using transformers. And because the new results are so amazing that we are actually trying new horizons and trying new experiences. And you can see this. We can see this objectively on the GLUE dataset. So GLUE dataset is one of the most popular NLP benchmarks out there in research, especially. And what GLUE is, it's a set of 11 NLP tasks from paraphrasing, sentiment analysis, detection, etc. And it will give a final score of your model. So if it's good in all of them, your final score, which is the one that you're seeing there, it will be high. And now you can see that all the top places, so we have Ernie, Structbert, T5, Electra, etc., they are all transformers. And then the best LSTMs, the best RNNs are placed at 29th place with a score of 70, while the first place is now 90. So there has been a big jump in performance since they use transformers. And so from there on, it has become a race on who can publish the bigger and better transformers. So you can see that not only the number of transformers is now that's now published is increasing, but also the size of them. So on the y-axis here, we have the number of parameters in millions. So OpenAI GPT, which is one of the first to use transformers, has 110 million parameters. BERT, which is now one of the keystone or the biggest, like let's say the de facto base transformer that now everyone is based on, has 340 million. Megatron from NVIDIA has 4 billion, and now OpenAI GPT-3 has 175 billion parameters, which is a monster. It costs like $40,000 just to train it once. So, but it gets superhuman results. Like you can give it a sentence saying, "Hey, give me a website that looks like TensorFlow, but for a mobile app," and it does just that. It gives you the HTML code for that. Or, "Hey, make me a neural network for a binary classification task with dropout and data augmentation, whatever," and it will generate for you the Keras code. So it managed to get really awesome results. But now it also made a problem. So why do they manage to get such good results? Well, let's see the pipeline of training a transformer. And from there, we will see the problem. So to start, we need a big raw data set. So we need a big data set of raw text, to use for unsupervised. So no labels, just raw text. And then we get an untrained model. Now, usually what we do is we take a labeled data set with, let's say, sentiment analysis, or positive, negative, or classification, and then you train a model on that. However, they found that by doing something else before that, we get tremendously better results. And that thing is what we call pre-training. And pre-training, as the name implies, means a step before actually training a model on a supervised task. And it's actually a replacement for the random initialization of the weights. So usually we have a randomly initialized weight, and from there we try to train it, so to update the weights. However, in this case, we want our model to start the training with better weights, and that is accomplished through pre-training. And so what pre-training does is that it's training the model on the big data set, which is raw, on autocomplete and fill in the blanks tasks. So it takes the words, and it's like self-supervised. So the text is in itself text and labels, And so the model has to learn the distribution of words across the text and know which word comes before and after other words so that it can suggest the best ones. And so in this case, a really well pre-trained model is one that can give you a number of awesome suggestions for a given sentence, like hello, my name is, well, James, long, too, easy, very, also are all possible candidates. And the same goes for the fill in the blanks. If your model can suggest something like this, then it's a well pre-trained model, meaning that it has learned really well the underlying patterns in the raw data set. And we can see this even better by taking the embeddings. If you remember, we talked about embeddings. By taking the embeddings of all the words that it learned, so for each word we will have a feature vector, and you can map them, project them on a 2D plane and map them, we will get something like this, which is basically a 2D representation of all the feature vectors, and you can see the words that have this nearly same vectors are near together. And you can see this example for prism, prisms, mirror, reflector, reflectors, which are all in the same category. So for the others, we might find the pronouns, verbs, adverbs, etc. This shows that the model has really well trained on the data set. It has learned and understood the language. So we usually do this on a raw data set, which is general. So if you want to make something for English, you would need a big data set of just English articles or text, whatever it is. If you want it on your own language, you do the same thing with your own language. When your pre-trained model is giving really good results, now you can get some smaller specific task data sets which are supervised, so sentiment analysis, paraphrasing, classification, and then you make copies of the pre-trained model to do what we call fine-tuning. So now we are going for the real supervised training, which is called fine-tuning, where you get a pre-trained model as an initial model instead of something random, and then you fine-tune the way so that it only changes the small difference that it needs, so that you can get task-specific models or fine-tuned models that are ready to be used for your tasks. So this is what you call this is what you specially use for transformers. This is all the pipeline, and this is why transformers are now getting really good results, because the models are so big, they can learn well on big data sets for the pre-training phase, and then you can use them for the fine-tuning. And this has allowed these models to get way better results, as we've seen in the glue data set. But that's also one of the downfalls. So here's the problem. These are some examples of the most popular transformers by 2021. So let's say by middle of 2020. And these models have pre-training data sets, raw text of at least 13 gigabytes. And please do remember that text is very compact. 13 gigabytes of text is not the same as 13 gigabytes of images and videos. You need a lot of text to get 13 gigabytes. And so you would need at least that to train a model to get superhuman results. And for some languages, that is not a problem. As you can see, most of these are in English, Arabic, French, you might find in German, Italian, Spanish, but these are popular languages with so many online speakers, so much content in those languages. However, according to the Linguistic Society of America, there are 6,909 distinct languages, and according to the Endangered Language Project, more than half are endangered, meaning less than 1,000 speakers. And this is not even taken into account dialects. So if you are working on making, let's say, an emergency chatbot, or you want to make something that is specific to your own country, to your own dialect, and there isn't a lot of content online to make it, like for example in our case with the Tunisian dialect, well, this may cause a problem because you cannot get enough data. You need gigabytes of text, and yet with all the scrapping you did and everything you managed to do, you still could not get anything. So this is where data augmentation can really be a lifesaver. So you might not be able to buy more data, so you need to do with what you have. And so data augmentation, this is where it can really help. And for those of you who don't know, data augmentation is a technique that allows us to create multiple copies of the same input data point. For example, an image can get rotated, translated, skewed. We can up and down the resolution, and the computer would not know that it's the same picture. So it's learning from that. And we do this, we can do like even 100 copies of the same picture. But data augmentation has till now been mostly used in computer vision. NLP has not seen the same amount of interest in it. Why? Because most research is done on the popular languages. So if you want to do something in English and German, French, etc., well, there is no problem. There are there's so much content, so much data, and so many people working on that. While you don't have that for your dialect. So most of research is not concerned with data augmentation for NLP because they don't need it. And in the case of computer vision, pictures are the same wherever you are. So be it, there's no English picture and Italian pictures, it's pictures. So data augmentation is a need for everyone. So everyone is using that, it's good. But NLP, only those who work on non-popular languages with not much content are the ones who are suffering. So that's why there's not a lot of work into that. Well, however, well, there are still some good attempts, and that's where what I'm going to show you now. I managed, so in my work, when I wanted to make a transformer work on the Tunisian dialect, which had less than 200 megabytes of online text that I could find and scrap legally, I had to use data augmentation. And I've been through a number of techniques that I've found, and I'm going to try to share with you these techniques and the GitHub link so that you can use them in your own project. So starting off with the easiest way to use data augmentation, it's called EDA, or Easy Data Augmentation Techniques, for boosting performance on text classification tasks. It's a fairly old one, and what it does, it introduces 4 operations that is done on each of the sentences of your data set, and these 4 operations together can create up to 9 or 12 copies of the same sentence. So how it works, you have a original sentence, like the first one is the stable, a sad superior human comedy played out on the back roads of life. And you have 4 operations. The first one is called synonym replacement. So as you can see, sad has become lamentable and the back has become backward. And then we have RI for random insertion, meaning that we randomly insert a word into the sentence, like the word funniness. RS stands for random swap, so we swap 2 words like the and roads, and RD for random deletion, meaning we randomly delete a word off the sentence. Now, some of these do help, and it also depends on your type of problem. If you are working on chatbots, for example, well, this might be interesting because users generally make these mistakes. They forget the word, they swap words, they make typos, they make a lot of some problems. And so this might be interesting to let. However, if you work on something where this type of problems are minimal, like research, scientific research, or medical field, well, maybe you don't need a random swap, for example, or a random insertion. Do, however, note that the synonym replacement is done by what's called GraphNet, which is a dictionary of the English languages containing synonyms and antonyms, and that has helped. That has been, first of all, maintained for many years and has been used in the EDA project to make that. So if you are not working on the English language, this may be a problem, but there's no problem overall because you can just easily go into the source code and just remove the synonym replacement part. Now, do note, the authors showed us that the less data you have, the more efficient it is, and it's actually really reasonable, because the more data you have, the more likely you are to have these sort of problems and variations of the same sentence. The less data you have, the less likely it is that you have them. And that's actually why data augmentation in NLP is not really interesting for many, because if you manage to get gigabytes of text, you are sure to have so many variations of the same text somewhere in it. And so they don't care a lot about that. But for those of you who work on dialects and text and languages with less text, like my case, no, this can be really helpful. And I actually use this in my work, and it did help us, even with just random swap and deletion. So this is the first one. It's available on GitHub. It's called EDA NLP by Jason Way 20. Just check that afterwards and see if this may be helpful for you. The next thing is also really interesting. Ever, it's actually uses the already established and trained models to try to translation services and try to use them for your own sake. So back translation means you take an input original sentence, like I have no time in English. You translate it to another language using a service, like an online service like Google Translate, for example, into French, je n'ai pas le temps. And then you translate it back to English, I do not have time. And you see that I have no time, I do not have time, are different techniques, are different sentences, but they have the same meaning. So this might be a good idea if you are working on some languages that are still popular, and if you work on translation, you can use this for many languages and try to get really high quality sentences to augment. However, it's also luck-based, because many times the same sentence comes back the same. So it's luck-based for this one. All right, so now you've seen the EDA part, which works on rules and dictionaries, and back translation, which is based on APIs. I want to go back to this part. I want to go back to the part where our model is trained for autocomplete and fill in the blanks, and it will have learned a good representation of that text. And why I want to go back to this, because technically, if you see the suggestions for autocomplete, they are all plausible and they are all logical too, meaning that there is somewhere a context where we might use these other the differences. And this is interesting. We might use this. If you've done a Google research before, you might see something like this. What is the weather? And it gives you so many different auto-completion suggestions. And this is interesting. Technically, behind it, we have what's on the right, a dictionary, well, in our case, an inference from a trained model, where you give it the input sequence, and it gives you a number of suggestions which can be, which are all plausible. And so technically, we can use this top words prediction from a trained model as a way to augment our data. And how we do that? Well, first we need a pre-trained model in a certain language, and then we can either do swapping, which means we take a random word. The word in NLP is called token. So if you have a sentence with 4 tokens or 4 words, we randomly, or you choose however you wanted to do a token, and then we mask the token and we tell the model to autocomplete, to fill in the blanks with suggestions. Or we insert a token there, a mask token, and we tell it to either autocomplete or fill in the blanks, the same thing. And so doing this will allow us to create many copies of the same sentence, which are plausible suggestions because it has been trained on a model before that, so it's not random. And then yeah, for a second, let me just expand more on this. You will get a number of suggestions, but then it will depend. So the result of this, the quality of the predictions will depend on how well you trained your model and how distributed the words are in the original data set. So why I say this? Well, you might need data augmentation for a specific technique, like let's say sentiment analysis. And sentiment analysis, well, you will have a label And so if you have a label with your text, so it's not just a text, you have a label, let's say positive and negative, and you use, for example, a swapping technique, you might have the sentence being the actor is amazing, and you try to swap amazing with other words, and it will predict amazing, cool, good, bad, terrible, because they are all adjectives that can be used in the same context, which is bad for sentiment analysis because the original sentence is positive. So all the suggestions should be positive. Where if you have terrible as suggestion and it's put as positive in the label, well, that will become a problem. So what Suzuki Kobayashi has proposed is to use this same mechanism, but to add a small information point, which is, for example, positive or negative if you are working on sentiment analysis, or give it another information token classification. So basically, Suzuki said, if the original sentence is the actors are fantastic, and you want that to be something positive, so we can add a third information which is positive, to say give us suggestions that are positive. Well, in this case, he uses on actors, but if you use this on fantastic, well, we will be sure that the suggestions will be also in the same space, which are positive reviews. You can also use this in the classification part, like if you work on LDA, if you work on topic modeling. So what's the topic we're talking about? But how do you use it? I would suggest that you read the paper to see how they do it. So now, expanding on that, the idea of using top words prediction has become really popular because with well pre-trained models, we are getting good results. And so it has been then applied with not word2vec, but with BERT, which is one of the transformers in the second paper that you can see. And then the third paper has generalized that to any pre-trained transformer models. And so now it's not uncommon to use this technique with any transformer model that we have, or any model actually that we have. And I would suggest that you take a look at this library called NLP Aug. I will just show you around because I really like this library. NLP Aug is an open source library that does, as the name implies, data augmentation for NLP. And as you can see, there are many ways to do it. Actually, you can choose. Let me just go to the augmenter. You can do augmentation on a character level, on a word level, or on a sentence level. And even there, you can, for example, keyboard augmentation with a substitute. So simulate keyboard distance errors. So for example, if you want to simulate someone typing, a user typing on the keyboard, and sometimes they can make a typo, well, it will simulate that with this technique. Or OCR if you're working on something else. Word would be the same thing. You can use the WordNet graph if you're working on the English. You can use BERT or any transformer in this list to use that randomly, and you can use with TFE, the IDF, synonym, splits, etc., and the sentence the same thing. So it's really easy to use. I would suggest that you take a look. Let me just show you a small example of how you can do that. There we go. So you just need to import nlp-aug.augmenter, then you choose whatever you want, char, word, or sentence, and then you give it an initial sentence like the quick brown fox jumps over the lazy dog and a dot. And then you can go on. You want the OCR augmenter, substitute a character. So you can see that over became ovec. So it might be a typo. The same thing here, randomly. We can then use word augmenter, for example, with a dictionary. So if you have a real dictionary that you work on yourself, or for example, with word embedding, so word2vec with a pre-trained model, we can use the same thing with TF-EDF, or with a transformer like BERT and distal BERT. You choose your transformer and you do that with the insertion of a word. So the quick brown fox jumps over the lazy dog. Even the quick brown fox usually jumps over the lazy dog. This is also plausible result. There's nothing wrong with this sentence, so it's good. And you can check the rest yourself. It's awesome. It's an awesome library. and also used for audio, for signals. Now, this might be a bit weird, but technically audio is also a set of notes that come in sequence, so maybe you can use this somewhere else. But yeah, I'm not going to dwell on that. So going back here, one of the most popular and efficient techniques would be to do this. However, we go back to the same problem that to do this, you need a pre-trained model on your language or dialect. And if you are already working on a endangered language or a dialect with really small data sets, well, you might not be able to have a pre-trained model already. So this might also be a kind of a challenge. However, I do want to say that you might try to pre-train a model on the small data that you have, and then use a pre-trained model that has been trained on the small data that you have as a reference point to augment using these techniques the data. And then once you augment that data, you can use you can pre-train a new transformer on that bigger data, and it will try to learn better from that. I know it gets better results because that was the project I worked on. Now, I want to add a memorable mention because the last parts, with the last augmentation techniques were general techniques, which means that they can be used for any type of text. However, there are some cases where you can actually go even further and try to find the patterns underlying your data yourself and use that to your advantage. For example, the paper I'm going to mention here, which is called Learning Semantic Textual Similarity from Conversations. What they did is they are working on question answering. So you have an input, an output, and then another output. So it's like a conversation. And they said, hey, some of these inputs have been said multiple times with many people, and they have different answers. So technically, we could group the different answers to a same input and use that to augment the data. Meaning that if I want to make a chatbot for my use case, I can train the chatbot to I can train the chatbot better by giving it many ways of responding to the same answer. And you can do the same many ways to ask for a sensor for certain information using the data that's already in their data sets, using the correlations but that are scattered across conversations. So they did that. They collected all of the same answers to the same questions, and then they added the sequencing of the message history to add more robustness to it. And from there on, they managed to get better results on test conversations in the future, because now the model has many ways to answer to the same type of question. So this is one of the ways that you might have some underlying pattern in your data that you might not be aware of yet. So I really liked how they did that. I was just doing that also before jumping into pre-training and top words prediction, because that does not always give really good results. At the same time, it's costly in resources and in time. Transformers are not easy to train. All right, so with that, let's just summarize what you've seen. There are three big families of data augmentation in NLP. One is the graphs and dictionaries family, like EDA, so where you use a graph or a dictionary that you prepare yourself for synonyms, antonyms, filtering the words, etc. This might seem like a huge amount of work, and it is. However, for some case, you might get a huge jump in results improvement by just making 2 or 3 hours worth of dictionary and putting the most common word that you have. So it helps a lot. There's also the trained APIs method family, which uses a service like back translation, which is useful if you work on a language that's not endangered. So you do have enough content online, but not that much. And the last one is if you cannot make a graph or dictionary, or it's not recommended. And there is no trained API online that can help you. So then you go into training your own small model, do some top words prediction, and then use that for data augmentation, so custom models. I would suggest to try trained APIs first, then go for graphs and dictionaries, like small amount, don't go too much into it. Your language will change. And then going for top words predictions. And that's actually the way I tried it. You might find a better way in your own use case. All right. So with that, I finished my presentation. So thank you so much for staying, for following up to the end. And I'm now open for any of your questions.
Thank you for a wonderful presentation. Let's check if we have any question in chat. Yeah, it seems that people maybe don't think about any question or type them later in comments. I will let you know in Facebook or something. I also think that we will share some additional materials in comments or in description later, just to people better understand this topic and this approach.
Mm.
And yeah, I think that's it. If you have any question, don't forget to write comments. Don't forget to like this video and share with your colleagues and friends who might be interested in natural language processing. Also, you might check some video from previous events when we talk about different topics on machine learning and deep learning. And that's it. Have a nice day and see you all next time. Bye.
Thank you. Bye.